Hello everyone, welcome back to my channel, Deep Understanding of Research Papers. Today I am going to explain one very recent paper which was released to archive around 4 days back, called Multi-Source Domain Adaptation for Text Classification via DistanceNet-Bandits. And as you can see from the title itself, you can see this paper is from this paper is an NLP paper, basically the sentiment classification paper, but the concept is different. So you may think sentiment classification is a very well-known problem, but the reason why they are doing this domain adaptation is very interesting, and that's why I choose to do tutorial of this paper. And this paper is written by Han Guo, Ramakanth Pasunuru and Mohit Bansal from University of North Carolina, Chapel. So the tutorial is going to cover the overview first of this paper. Then we will see what are the domain distance measures. So if you are working in something called domain adaptation domain adaptation community on topics, it is applicable whether it's in NLP, computer vision or speech. It's applicable to all fields. You will know about these distance measures people use to do domain adaptation, and we will discuss some of them, and we will see how those distance measures are used in this paper. Then we'll see this proposed model for this text classification, sentiment classification, and how do they use these domain distance measures for adapting these different domains into the picture when you're doing testing. And we'll see the experiments, and finally we'll see this analysis of distance measures, and at the end we'll see some results. And this tutorial has around 20 slides. I think the tutorial is going to be a little bit longer than what I used to do before, because there are so many things we need to understand, like for example, like how this bandit works, or multi-arm bandits works, and all those things. So be patient. We'll start with the introduction. So basically this is about understanding or seeing how different distance measures are being used for domain adaptation. So basically the distance measure, when I say distance, you can think of it as comparison, right? So comparison between the samples from two different domains. Like for example, you have a, let's say, some source domain which has let's say sentences in the domain of let's say marketing, for example, right? Not exactly marketing. Let's take an example of maybe uh, let's say electronics, right? So you have electronic related sentences, and you know the labels, and you have another domain which is mostly about let's say something like movies, for example, right? So these two are different domains, because the when you are talking to a person who, let's say, you're selling an electronics item, the words which you use to sell those items to the person, electronic devices, so you will use different words, like for example Sony, Panasonic, those kind of words. And when you talk about movies, you will talk about the actors, actress, those kind of things. So these two are different domains. But if you train a model using electronics device data, sentiment data, and if you try to apply it to this movies data, this is not going to work. This is like very well known problem, because there is a distribution mismatch. So this electronic data will have some distribution px, and this will have some distribution py, so they will not be equal at all, so at any point in time. So how do you make these two distributions closer? So that is the $1,000,000 question. And if you can make them equal, then you solve the problem. And how do you do it? There are various ways to do it. There is a supervised way, there is unsupervised way. In the supervised way, you get some label data from the target domain, and you have a lot of data on the source domain, which is electronics, and you just fine tune your model to work on the target domain. Very simple, right? But you need the label. And if you come to unsupervised methods, there are various other methods, like there is something called DAN, which is basically known as the full form is domain adversarial neural domain adaptation, I think, domain adversarial neural network. So basically the idea is to use a discriminator to may fool the generator or feature extractor that the inputs are not from the source domain or target domain, so that the model, the feature extraction, learns robust features which are invariant to the different domains, right? So that's a very nice idea by, I think, Ian Goodfellow back in 2015. Then came something called gradient reversal technique. So this is one of the other standard technique people use when they are doing domain adaptation. And also a lot of people have used gradient reversal for NLP. Like recently, one of my friend who is in Apple right now, so she published one paper on using gradient reversal for question deduplication task. A very interesting paper. You can check it out. So it was published in ACL 2019. So that is one way, and there is something called Weserstein distance based DAN, basically the domain adaptation. Basically the GAN, it's the same sort of GAN idea, but they use Weserstein distance and all those things. So I mean, this the field is vast, and a lot of people have done a lot of work on this. And not only in NLP, people have applied this in computer vision, and people have applied in speech also. So I was also working on one of the paper to do something similar to it, but I have not published it yet. I think I'll publish it soon. It's a very interesting field, and you can do read more about this domain adaptation. Coming back to the tutorial, so you have two distributions, and how do you make it similar, or how do you come up with a model which is agnostic to different domains, right? That is a question. And this paper uses something called DistanceNet, which basically adds different types of distance measures between two distributions of the feature, and try to minimize those distributions, so that your model is agnostic to variations in domains, right? And we'll see how that is done. And there is a very interesting idea also called distance bandit model, which is basically how do you use multi-arm bandit setting while training distance net. Because if you have multiple domains, let's say you have 10 different domains, and you have label data for all those 10 different domains, how do you efficiently use those domains, use that data to train your model? So one simple way could be simply add up all the data and just train a very big model using all the data, but that is like a crude way of doing it. But how do you use multi-arm bandit setting so that you can use the reward functions, or you can use the the MAB to select a particular source domain, source domain, and a target domain will be known. You to select a particular source domain so that your efficiency is improved. So we'll see how that is done. And they show that DistanceNet along with bandit variant can outperform all the previously published baseline for this task. And now let's go in detail of what this paper is doing. Basically, what are the different distance measures they are using? Those are mentioned here. So one is L2 distance, a very simple L2 distance. We'll see how that is. Cosine distance, many people will be knowing. MMD, basically maximum mean discrepancy loss. I think many people will be knowing about this paper called moment matching networks. Basically generative moment matching network, which was published in 2015 by Kevin Squarsky and his co-authors. That paper is a very well-known paper where they introduced this MMD. I mean, MMD, they didn't introduce MMD, but they used MMD to train generative adversarial networks. And I also have a tutorial of this MMD, moment matching network, which explains MMD. You can check out my tutorial list. You will find this paper. You can read more about this MMD loss. And Fisher linear discriminant, many people will be knowing about LDA. We'll see how that is being used as a loss function. And then correlation alignment, also known as Correll. And mixture of distances, like how do you combine all these distances into a single distance measure or single distance function, and you can use that to train the neural network. And always assume XS is basically set of source samples, and XT is basically the target samples. So there are NS number of samples in train source, and NT number of samples in target, and this each one will be a single vector. So basically this will be the output of the last layers feature vector. So basically, if you have, let's say, convolution neural network, and you can use some sort of bottleneck layer, and when you feed an input, sorry, when you feed a words like sequence of words which is sentence, you get one vector here, so that will be one item here, right? It's a d-dimensional vector, for example. Just keep that in mind. Now let's go in detail and understand what are these distance. I mean, I don't have to explain L2 distance, very simple. You just compute mean of the source data and mean of the target data, and you just compute take the L2 norm or norm of the norm of these two vectors, you get the L2 distance, like very simple. And cosine distance, very simple. You know, you can just you know the mean of the source, mean of the target. You just take the cosine similarity, cosine distance, basically the cos function of these two vectors. This is very simple, and the distance will be 1 minus of that cos, so the 1 minus of that cosine score, right? Then coming to MMD, basically maximum mean discrepancy loss, we basically assume PS is basically the probability distribution of the source data, and PT is basically the probability distribution of the target data. So this MMD loss is defined defined like this. So f is basically a class of functions, and you want to find out a function f, which is basically the supremum from this class of functions, and you just compute this function, the expectation over x of the function with respect to xs, so on. And if you read the Kevin Squaresky's paper of GMMN, which is basically the generative moment matching network, you will find this function, which is basically assuming the kernel k, which is basically which is nothing but a simple Gaussian function, Gaussian kernel, which you can see it here, Gaussian kernel, and you just compute this entire function, which will give you the MMD loss. So this is actually proven in that GMMN paper I am talking about, like how they are using the Gaussian kernels to approximate this function by this, and this loss can be used to train your neural network, and minimizing this loss will make the distribution PS and PT much closer, right? So it's just like other loss function, like for example you have two distribution, how do you minimize the distribution, how do you compare two distribution? Like very simple one could be KL divergence, right, or Shannon divergence in case of generative adversarial network, or Jensen-Shannon's distance in generative adversarial network. But in the same way you can also use MMD, which is also sort of distribution matching loss function, and you can use that to train the generative adversarial network. That is another way, but you can go and read the paper for more details, like what are the advantages and disadvantages, right? So assume you have this function, and you know the k's, which are basically the Gaussian kernels which are with this function, and as I mentioned, this is actually mentioned in the Kevin Squaresky's and Rich Sammel's 2015 paper. And this is maximum mean discrepancy. And coming to Fisher linear discriminant analysis, I don't have to tell this to you because many people will be knowing about LDA. So basically you have let's say you have a data and compute SB, which is basically between class variance, and you have SW, which is within class variance. These are basically the matrices, covariance matrices, and you find out a W, which basically separates these two class very well, right? So that's what you want to find out, the argmax of this function, and this function is basically optimized to make the within class variance very small and between class variance very large, and you just find out that mapping where that W is doing that, and then use that as as the loss function for linear discriminant analysis, Fisher linear discriminant. So the loss function where this optimal W star you find, that is my my distance. Coming to Correll, basically Correll is another distance measure. Basically what they do is they just find out the loss or distance, square distance between second order statistics. So the second order statistics are nothing but the covariance matrices. So you have source data, you compute the basically CS, which is basically covariance matrix for this S source data, and you compute covariance matrix for the target data, and you just compute square distance. So this is nothing but the second order difference, or second order distance between source and target, and very simple loss function which you can use. And then coming to final mixture of distances, basically not just using a single distance, you just combine all the distance which we discussed below, like all the 5 distances with some weighting parameter alpha k, and you make that as the mixture of distance. And this is the function which we are going to use it to train our model basically. So we will see how that is done. Then coming to the model architecture, I'll show you what is the baseline model, then I'll show you what is DistanceNet, and then I'll show you at the end what is this multi-arm bandit setting for training this DistanceNet. So so the baseline model is a very simple model. So you have an LSTM which just takes sequence of embeddings. These embeddings are nothing but glove embeddings for every word, and you have number of capital T words, and you just tap out the final hidden representation of the LSTM. Basically you have LSTM, right? So you have sequence of words, and you have the last word, so you keep feeding W1, W2 and so on, WT. So whatever representations you get here, the hidden representation, you use that as our input to the distance computation. So basically you got it. So as I was talking about xs equal to, initially I was telling like x1, x2 and so on, right? These x's are vectors, which are these vectors. Or if you have a convolutional neural network model, you create a bottleneck layer and use that as that vector as the representation. Basically simple representation of the entire sentence, which could be a simple last layer's output, right? So as simple as that. Then since you have the labels, you can compute the loss function, compute the softmax, basically the label class, basically whether it's positive sentiment or negative sentiment, and you can compute the loss function using cross entropy, very standard cross entropy loss function, and use that to train the baseline model. So baseline model does not do any domain adaptation or anything. It's simply given a sentence, it predicts whether what is the label for that particular particular sentence, right? Positive or negative review, right? Now let's see the proposed model, which is basically the DistanceNet. So basically why they call it DistanceNet is because you have the cross entropy loss and you also have this distance loss. So what is this distance loss? The distance loss is basically the distance measures which we were discussing about, right? So what is that distance measure? So we had a lot of distance measures like L2, Correll, cosine distance, MMD, FD, so FDA. So those are like we had many distance measures, and this distance is actually computed using one of the 6 distance measure which we talked about, right? How do they do that? You have source input, which basically have the labels, right? And targets, we don't have the labels. So the source inputs are basically a set of sentences, and along with their labels you feed it through feature extractor. In our case it's an LSTM, and that gives you one vector called H source of T, right? For if you have one input, and you do the same thing for target input. Basically the target input don't have don't have the label, so basically that is going to be T, right? HT capital T, for example. Let's make it a small t, right? So these are the vectors I have. Now we have to compute the distance, right? Simple, I'll use one of the 6 distance and I'll compute this, and as a standard cross entropy loss I can compute the cross entropy loss for the source predictions, which is the simple loss function here, and you compute the distance measure between the source and the target, and you can scale it by some beta, just some regularizer, and then you can train the model. Very simple, right? So nothing big deal. So nothing fancy architecture or anything, just LSTM, and job is done. Okay, so this is the whole idea. So what is the contribution of this paper? You can say there are so many distance measures they are using, and there is a mixture of distance also which combines all the distances and just does the training. That is the contribution, and not just that, there's one more contribution which is basically, I would say, a novel contribution of this paper, basically using something called multi-arm bandits for training the model. So what is multi-arm bandits? So basically, I mean, multi-arm bandits itself is the biggest field by itself. I mean, people have written books only to learn this bandit algorithm. So it's not an easy field. It's heavily mathematical driven field. If you want, you can go and explore it. If you want to become a master at it, you can. There's a very famous guy called Shaba Sapavari something. I don't know how to pronounce that. Just search for Shaba, so you will find a big blog and his book also there on how do you do the bandits. Basically, how do you learn about these multi-arm bandits? And he's written a lot of algorithms on multi-arm bandits. Very well known guy, and I just read about it, and I just I will just tell you like how this is done, and you can just also see some of the tutorials for learning this multi-arm bandits. So what happens is you have lot of source data. Let's say you have 15 domains, right? S and you have one target domain. Now, how do you do the training? So, if you know, if you have only one source domain and one target domain, things will be much easier. You can use just the simple distance net and just train the model, and the model should perform very well on the target data. But in our case, let's say we have 15 domains, which are all source domains, right? Now, how do you use it? So, one way could be just combine all the 15 domains data into a single data and just do the training with all that 15 domains as a single source domain. That is a very crude way of doing it. I mean, you are not efficiently using the resource, and if you are not efficiently training the model, so other what you could do is you can use multi-arm bandits. There are other ways of doing this also. You can use Bayesian optimization and so on, using, since you are getting the reward function, you can use Bayesian optimization, but this paper uses this MAB methods. So what you do is you just select one of the source, one of the class, one of the domain in the source list of source domains, and you take the target fixed, which is known target input, target domain. You just feed it and you do the normal DistanceNet training, right? Then you evaluate with a fixed set of evaluation data, and that will give you some accuracy, and you use that as the bandit reward, right? And just to draw some random stuff, I mean, assume this is your uh, reward function, and you don't know this reward function, because if you know this reward function, you can directly calculate the gradients, but you don't know the reward function. So as and when you do the training, what you get is these points, for example, right? Accuracy, these are accuracies, for example, these are rewards, you get these points, and based on this you can select the next point you want to sample, the next data points, and you can compute the reward function, and you can keep doing it until you find the one which is basically gives you the highest reward for this evaluation data, and you can use that during you can use that do the training with that kind of data set. So how this looks is like, I mean, I don't want to go in very detail, you can just go and read about multi-arm bandits. This is like, for example, let's say you go to a casino and there are so many machines which you can play with. You can give some put $1 and get $100, and you can keep playing. It's like if you go to casino, you will experience this. But in this case, they are using something called UCB, so upper confidence bandit algorithm, which is 2002 paper, I think, and they're using this function to do the training of this multi-arm bandit setting. And you can just read more about these paper, I mean these multi-arm bandits models in online. There are so many books available, and Shaba has a lot of resources like tutorials and all. You can just go and watch them. And coming to the experiments, as I said, they have 16 data sets. About most of them are about product reviews, movie reviews, and so on. And they just say whether it's a positive or negative review. And they use 3 and 5th evaluation data set for the evaluation. And they use a single layer bidirectional STM for training. It's an encoder. And classification, they're using 2-layer fully connected layer. And as I said, over embeddings, they're using glove embeddings. And and as I said, to train the multi-arm bandit, they use some small evaluation dataset, and they compute accuracy on that, and that is being used as a reward function, right? Coming to the results, I mean, I honestly telling you that paper, those guys have done heavy number of experiments and analysis. It's like very thorough. You can just go and read the paper. Here I'm just putting like not all of them, I'm just putting some of them just to save time, because I'm already crossing around 25 minutes, so I'll just go through fast. So basically they have, as I said, they have different distance measures, and they can compute the the accuracy with respect to uh, different measures. But this here I'm not showing the accuracy. Here they are showing something called different ways of analyzing the efficiency of the model. So basically how they are doing it, the same method one basically is basically uses this equation, which basically tells you compute distance between two vectors or two inputs from the same class, and check if it is less than distance computed using the same class and different class or different domains, for example, right? And these numbers are like bigger for L2 distance and lower for Corel, and same thing you can do with method 2 also. This is the result, and you can compute correlations between two different vectors and so on. So it's just analysis. And coming to the accuracy numbers, so you can see here DAN is basically the, as I mentioned, domain adversarial neural nets, the Ian Goodfellow's paper, and keeping source domain as MR. I don't know, maybe this MR is the name of a dataset, and keeping A, basically A is basically April and B is baby. They are different datasets names, I think. And what is the accuracy numbers? And if you see the mixture method, basically combining all distances and training the model, gets you the state of the art. And this is the numbers for using, I mean, comparison between the multi bandit setting and normal setting. And as you can see, bandit setting gives you the best accuracy. And that's all for this tutorial. Thank you so much for watching this tutorial. If you are not subscribed to my channel, please subscribe. If you like this tutorial, please give a thumbs up. Thank you.